I want to finish up a couple of things about ordinary least squares regression. Last class, when we looked at an example, I showed you the printout from SPSS, and it was, we're really interested in the coefficients because we want to know the slope of the line. We want to know if the direction of the slope is positive or negative. And because that is a statistic that we're estimating from our sample, just like a z-score, we have to use our hypothesis testing framework to see if that coefficient really is different from 0 as we had in the null hypothesis. So when you get your output, you tend to look at, again, the slope of the line, whether or not that slope is statistically significant and therefore different from 0. What I want to do now is I want to introduce you to another statistic that you can generate in ordinary least squares regression. It's called R squared. Now, R is typically a measure of correlation, and we've skipped over that a little bit in class because, like I said, the textbook takes you down this path of ANOVA, which is analysis of variance, and it does so in a correlation framework. Psychology is really big on looking for correlations. But I'll tell you that correlation is not causation. And so in political science, we tend to stay away from that framework of correlation. The other reason that psychology in the medical field likes correlation a lot is because they're solely dealing with people. Psychology professors aren't doing research on when nations go to war. So for correlations in people, it's much more of an accepted, I guess, argument that when you see high levels of correlation in people, you're willing to believe causation. But in political science, we're really skeptical to that idea of causation being proven by correlation. R squared, simply put, is a measure of model fit. Right? How well does your independent variables explain the spread or the cloud of your dependent variable? R squared is, going back to the way that Lagrange talked about it, the explained sum of squares divided by the total sum of squares. And what you have in here to compute it, again, not really difficult math, right? You got a summation sign, you got a subtraction sign, you have an exponent, and you have division. How do you compute? Well, yi is the observed dependent variable. So that's our data. Y of I is our data. Y hat is what we can predict that the data point should be. So y hat is our predicted value. Where does y hat come from? Well, it comes from that original equation. Y hat, you take the intercept or the constant that you find, and you add beta 1 times x1, so you have your independent variable for that. You multiply that by beta, and what do we assume about the e? We assume that your errors are 0. We know that's not true, but we assume it, right? The e just kind of goes away. So that'll give you y hat. So that's the difference in what we've predicted divided by the difference in that observation from y bar, which is what we would expect, right? Because y bar is what you expect. That's your sort of default guess. like my wife's age was a default guess of the average age of all people. So we have here a measure of the difference between what our model predicts versus what you would just guess. Right? And that's represented as r squared. R squared is going to be a value between 0 and 1. Okay? It'll always range between 0 and 1. Now, what do you think is better? A higher r squared or a lower r squared? What do you think's better, right? So this is a measure of model fit. What's better, a little r squared, like 0.1, or a really big r squared, like 0.9? Why do you think it's a little one? Okay, a better fit. But we're measuring fit. R squared is the measure of fit. And it's got to be between 0 and 1. So would you rather it be low or high? Let me rephrase this in another way. I give you a test. Do you want your score to be low or do you want it to be high? You want it to be high, right? You want it to be like a 98. You don't want it to be a 10. R squared works the same way. Because what it is representing is the percentage of all of that variance in the cloud that you're explaining by your independent variable. All right, I'll give you a few examples so we can really get this home. But again, this is where math is like magical again, right? Because again, we're working with a framework where our numbers are bounded between 0 and 1. Kind of like what? What else is bounded between 0 and 1? Thank you. You learned something. Yay, Tom learned something. The area under the curve. What else is bounded usually between 0 and 1? Probability. Oh my God. It's all coming together. I'm going to cry. All right. This is all coming together for you guys. Math is magic. It's filled with amazing coincidences. All right. So here's a scatter plot. It's probably something silly like the number of hours you spent studying and your score on a test. I forget where I steal these from sometimes. So this would say what? Right, the more you study, the higher your test grade should be, right? And if we were to see this data set, 2, 4, 6, 8, 10, 12, I got like 16 students. And you come into the exam, and I ask you before the exam, so how many hours did you study for this exam? Okay, and I write that down. And that's my explanatory variable. And then you sit down and take the test, and I grade the test. And that's my dependent variable. I've done this a few different ways. One time I ran a correlation between how long you spent taking the exam with your grade on the exam. So I gave everybody the test at the same time, and then when they turned the test in, I wrote on their test how many minutes they took the exam. What do you think that looked like? Do you think that looked like this? Where the people that took 10 minutes on the exam scored really low, and the people that took like 3 hours scored really high? Why not? No. Sorry, all right. So so the theory is, right, if some people just know it, they can probably just take the test quickly. You sit down, you're like, I know this. Done. And you're like 10 minutes. Have you ever taken a test and you're the first one done, but you don't want to get up because you're like, I don't want to be that guy? You've had that feeling, right? Or you've taken a test and somebody's gotten up after 5 minutes and you're like, what the hell? Sit your ass back down. You don't know that much more than I do, and I'm on 2. Right? You've had that feeling, right? Well, right, we could have a theory that says that the longer you take on an exam, right, the more time you take, it should increase your score because you're taking the time. But we know that maybe taking all the time on the exam is a sign that what? You really don't know anything, right? So that's a theory we could have. And we could test that theory. And if we ran it like an ordinary least squares regression, well, the first thing we would do when we had that data is create this. We'd create a scatter plot. So when I did that, I created the scatter plot of time that it took to take the test. It was actually it was really weird because there were a bunch of dots up here, and there were also a bunch of dots down here. And I'm thinking, well, maybe it's not linear. And it wasn't. It wasn't linear at all. Just some people take a long time and some people are quick. There was no correlation. There was no slope that I could draw that wasn't really a zero. But it did anger me, and I did make that class sit and wait like half an hour before they got up. So here's hours studied and your score on the test. And we do the scatter plot, and it looks linear, right? It looks like it should be a straight line. So where would we draw our line? Yeah, it would be in between, right? Okay. Should this have a pretty high r squared or a pretty low r squared? Why should it be a high r squared? Yeah, because the scores are really consistent, right? And that line, yeah, it's, you know, it's not directly through the dots, but it's pretty close, right? You're just going to have little tiny errors. So as you're doing that equation for r squared, right, this gap here between what is predicted, because this is your predicted line, and what is observed, all of those numbers are going to be really, really small. But what would the average be? Right? So we start our dots around like 55, and our dots go up to 95. If I were to draw a line through this that represents the average test score, where should I put it? Think about that again. Somewhere between 55 and 95. Thank you. You took a step back, Joey. Okay. This is our y bar line. This is our y hat line. What are the errors going to be in that y bar line? Really? So from here to here, that's 0? They will cancel out if we sum them all up, which is why we do what to them? We square them, right? Because we don't want them to cancel out, so we square them. So that's where the squares part comes into the ordinary least squares. So if you look at this line, right, from there to there, that's really big, right? So you're going to have really big gaps between what you predicted by using the mean and what you observed in the data. Is that a question or you're stretching? All right. So this is why the line is so much better. The line, the regression line, the y hat line, is better because A, we're trying to guess based upon an x variable. Right? So by adding this information into our data set, we're going to see the relationship, and we're going to say, that looks linear. I probably should draw a line through it. Once we draw the line through it, and that's where coming up with those coefficients, those betas, right? The betas tell us the slope of the line. Then we need to know how well does our line do? How much better are we at guessing my wife's age by knowing my age? Or how much better are people going to do on an exam if they just studied more? All right? I love it when students in like POLI 201 come to me And they're like, Dr. Wood, I studied so hard. I'm like, really? What do you mean hard? I'm like, for 2 hours I studied. Where's 2 hours going to get you on this? 2 hours is going to get you like 65, 70. 2 hours isn't going to get you a 90. This is where relativity comes in. Like, to you, 2 hours was relatively a long time. And to me, 2 hours is, well, that's nothing. Right? How many of you have spent, like, a whole day studying for a final exam? Or multiple days? Yeah. Your hours are way out here. And you're going to do better. And the people that, oh, man, I studied so hard. How hard? Well, I looked at the chapters about half an hour before the exam started. See, this is where measurement comes in. Because if you told me I studied for a really long time, I would say, what the hell were you doing all that time? But it was hard for you to sit down and read for half an hour. This is more about you and your study skills than it does about me and the test that I made. If you think that's hard, yeah, no. Just no. Right? So we have a theory, the number of hours. One time I had a theory that students that come to class should do better on the exams. Right? So if you come and listen to me talk, and I make exams based off of what I say in class, you should do better than the people who just read the book or just look at a study guide and do some Googling. And so what I did was I took a student's, this was in POLI 201, I took the number of absences that they had and their test scores. Now what do we think, so if this is their test scores, and this is absences, what do you think that line would look like? You think it would be negative, right? So something like that? Yeah, it was. Every absence was worth, for that class, on an exam, every absence was worth 4 points on the exam. So after 3 absences, how many points have you lost? 12 points. That's like a letter grade and a half, right? Depending upon where you fell. That was just 3 absences. So then for a couple years afterwards, I said, oh, by the way, you can put your hand up. I won't call on you. You got to stretch. I said, you know what? You missed class yesterday. That's 4 points. And of course, freshmen being freshmen, what did they think that I meant? That I literally already took 4 points off their grade. No. I was sick. It's an excused absence. I said, no, it's not that. It's that I expect you to lose 4 points on your exam because you missed class. And they're like, huh? Can I make those 4 points up? I'm like, okay. So I stopped doing that. Because I'm like, you people clearly don't understand, freshmen, right? What I was trying to tell you is it's important to come to class. And I know because I've run the numbers. And it's about 4 points. But now you've heard that I've taken 4 points off your test. And I don't want to talk to your mom about the color of your poop. Like, just leave me out of this. Actual conversation I've had. Okay? So there is really something to be learned by thinking about, thinking about data in this way. All right, back to R squared. Okay, so what is R squared? R squared is, as a percentage, or as, that magical between 0 and 1 number, how well our line fits our cloud of data. Here's some regression output from that previous scatter plot. I did this in Stata. And the coefficient for hours. So every hour that you spent studying is worth how many points on the exam? 6. Okay. If you don't do any studying, if your hours are 0, what would we expect your score to be? How many hours did you study? What's 6 times 0? So what would we expect your score to be? No. Why 55? What do you think 55 represents? 55 under the old high school version is that y-intercept. We call it the constant, right? That's beta 0. Beta 0 is where are we going to start from? So when x is 0, we're going to be right around 55. And then that's going to be where our line starts. And then as we go up by hours, so if we go up 2 hours, how much should we predict to increase by? If we go up 2 hours, we should go up 12 points. So from there to there. Why 12 points? 2 hours is our value of x. Our beta is 6. 2 times 6 is 12. Plus beta 0, which is 55. 12 plus 55 is 67. That's where we should be with 2 hours of studying. Okay? Okay. So here's our betas. This is beta 1, this is beta 0. Now, this t-score is the test of whether or not this 6 should be what number in the population? It is the slope. We know that. But if we're doing a hypothesis test, right? Because when you calculate a t or a z and then you look at the probability, what is the null hypothesis about our slopes? That there would be no relationship. So what would the slope be? 0. Okay? So again, in your mind, you're thinking, okay, there's a distribution of slopes. It's 0. I got 6. How likely is it that I get a 6, right? My beta 1 is 6, if the true value is 0? Well, we got a t-score of 25. Is that greater than our usual 2? Yeah. And how likely is it? It is very, very, very unlikely that you would observe a 6 when you should be finding a 0. Very, very, very unlikely. This is a 3-star kind of result. You'd put 3 stars next to the coefficients because it's that significant. 0.001. All right. So what would I say? Well, the number of hours that you study for the exam has a positive effect on your test scores. For every hour you study, you will receive an additional 6 points. Does that mean if you study, let's see, we start out at 55 and we want to get an A. So how many times do we have to, how many points do we need to get an A? 40. Jeez, just giving away A's, like a real good A. See, you guys are thinking like a student. You're like, what's the minimum I gotta get? Like a 90 or a 91? It's the minuses you guys really want. All right. So let's say we're aiming for a 95. That's a good solid A. Okay. We got to go up 40 points. How many hours do we have to study to get 40 points? 40 divided by 6. We got to study like 7 hours to get your 40 points. So, Dr. Wood, what does it take to get an A on the final? About 7 hours. Right? Come on, nod and show me that you're acknowledging this, right? Does that make sense? So some stupid freshman's going to go back and lock themselves in the library for 7 hours because they believe, but Dr. Wood, you said if I studied for 7 hours, I'd get an A. No, it's not what I said. Because that's not causation. Correlation is not causation. You can't study and then automatically earn that grade. Right? You don't present me with a time card. Like the librarian said, I studied 8 hours, therefore I should receive the fountain. No. Right? This is where, again, correlation, which is what we're seeing in our data, is not causation. You can be really, really, really stupid and study 8 hours and still not even get like a 55. Right? So when you tell me you worked really, really hard, that's nice, but working hard and studying for a long time does not guarantee results. Correlation is not causation. I have to do this all the time with my students that take the LSAT exam. They're going to law school, and they come to me and they say, Dr. Wood, I worked so hard. I'm like, okay, I took so many tests. I spent so much time on it. That's great. Correlation does not equal causation. You did the work. Right? You made yourself more likely to get a higher grade. The problem is that the LSAT is an aptitude test. Practicing does not make you smarter. It doesn't. It makes you more likely to unlock your, level of aptitude, but it doesn't make you smarter. Because correlation is not causation. So I pulled some other graphs of R squared from the internet to show how our model fits. Now the R squared from that last one, right, should have been really, really high, and it was, right? So here's our R squared from that model. How can you interpret this? 97% of the variance in that cloud, which really wasn't a cloud, it was just 2 dots around a line, 97% of that variance can be explained by the number of hours studied. That's a lot. Right? Where's the other 2.07%? Right? Because I want to be a completist. I want to know all of the reasons why people, get a certain grade on an exam. Where's the other 2%? You could just say it's error. You could. What other variables? Yeah, the amount of sleep they got the night before. What else? Think about when you've taken an exam, other than preparation for the exam, what has affected your grade on the exam? I don't know what to call that. Let's call it good student. Format of the exam. Can I use that? I'm really not good with multiple choice exams. Okay. Yeah, I'm hungry.
Come to the bathroom. That's a huge thing. Like some teachers say you're not allowed to come back if you leave the classroom. You have to use the bathroom.
You have bathroom anxiety.
That-
I think that might, whatever grade you read it.
So the pressure, right? I need to get a 94.6 in order to pass this class. Right? That's a lot of anxiety, right? That's a lot of pressure. Anybody else have any other excuses that you'd like to give? Any lame excuses that you've given a professor before? Okay, so let's throw in there, you kind of already know this stuff, right? So some people either just know it, all right? And so you don't need to study for 6 hours because, hey, it's just math and I can do math, right? And he gives me a equation sheet, something like that, okay? I've had breakup. I've actually witnessed this. So I had a student take the LSAT and bombed it. And I get the LSAT grades and I'm like, hey, dude, what happened? My girlfriend broke up with me the night before I took the LSAT. And I'm like, was that a good thing or a bad thing? Because sometimes breakups are a good thing, and you're like, yes, I'm free. And he's like, I loved her. I'm like, all right. You give them the reassuring, like, here's a box of tissues, dude. What happened? Finally, a few weeks later, a switch gets flipped. He's over it. I'm so glad I'm not with her anymore. Finally. Retakes the LSAT, scores 15 points higher. That's a lot of points on the LSAT. He really bombed it.
Well, like under 140.
He went from like a low 140 to like a high 150, close to 160. Just because it was girlfriend. That's the, ex-girlfriend, yeah. Okay. So I have seen this with my own eyes, right? You all have taken tests, and if I gave you a model, right? Some professor says, listen, your performance in this class is completely in line with your absences. And you'll be like, dick. The real reason I didn't do so well is because of you. Because of your, whatever. You didn't put notes online because the format of your exams. Because you wouldn't let me take the exam on a different day when I had 2 other exams and a paper due, right? You wouldn't let me go to the bathroom. I had to sit there and worry about peeing myself the whole time. So there are lots of other explanations that are out there. Here's the great thing about OLS regression. We can keep putting variables in. Okay? We can keep doing all sorts of variables. We can have 10 variables. And as long as and this is where something that looked really, really small and insignificant earlier in the semester, this is where as long as our number of observations allow us to have an appropriate number of degrees of freedom, then we can add more variables. Because every time you estimate a statistic, like that beta for hours, you're taking away a degree of freedom. So you can't have more explanations than you have data points. That won't work. The math will just kind of like puke all over itself. It'll just go, blah, I can't do this anymore. And no amount of calming down is going to convince that model that they need to get up, get themselves together, and go puke in the bathroom. Right? So you really can't force more explanations than you have observations. We're getting pretty close, right? We've got 2, 4, 6, 8, 9. We're up to 10 now. The model would do it, but man, it would really start to get a little shaky on us and say, pull over the car. Okay. So when you look at a series of different models, you can see that the better the R squared, the better that the line fits the cloud. So if you look at these two with an R squared of 8, that's 0.8, that's really good. An R squared of 0.24, that's a little weak, right? Yeah, the line has a slope, but you know, if I were to draw a different line through here, you would probably be convinced, oh yeah, that line's fine. But that is the actual best line to go through that cloud of data. But that variable, temperature, only explained 25% of whatever this revenue thing is. Here's another one. This R squared, 0.65. Pretty good, not great, right? You've explained 2/3 of the variance, right? It appears that there's a negative slope. Okay. I just did this one because it was Beer's Law. I have no idea what it's about, but it had a neat title. And if you look, yeah, that's a really good fitting line. Granted, you only have 6 data points, but 99%, 99.5%. There's very little out there that you can add to this as an explanation and have it influence the amount of fit that you have. I also want to note that this looks like garbage because it was done in Excel. It looks like garbage. All right. This is nice and pretty. This was done in Stata. This is the best looking one. This was probably done in R, which is the hardest program to learn how to use. But man, it makes really nice, pretty graphs. For the most part, I think Stata is pretty good. I can turn these things off. Like I can turn the blue background off, and I can make these lines go away. But Stata is really neat because like this is a green dot. There's like 600 options of dot color, and there's like 80 options of dot shape. Like, you want 5-pointed stars? I can give you 5-pointed stars. You want them to be red on the outside and yellow on the inside? I can do that in Stata. Okay. So that's our R squared. I don't have my phone. What time is it? I got like 5 minutes? All right. Now, OLS is great. Like I said, it's easy enough to do that you could do it by hand. It'd take you a really long time, but you could. But it really works best only in a limited sort of set of circumstances. If this were a 2-credit stat sequence, the next class would be how do we do this idea but not with OLS. So one part of the class would be, well, if we violate some of the assumptions, how can we fix it so that we can still have this great model with a cloud and a great line that goes through it. But this is only a 1-credit sequence, or 1-class sequence, so if you did go on, this is where you would pick up. First of all, one of the assumptions that we make is that the independent variable itself isn't really random. And what does that mean? Well, it means that there is some causal mechanism behind the independent variable that has an influence on the dependent variable. What's the best all-time example of a random independent variable that should have no influence whatsoever on what you're studying? Swiss girls' work. Scottish women's unemployment. Swiss girls' work. No. Scottish women's unemployment. All right, this is a joke from a class that I took a long time ago. We were trying to come up with an independent variable that would be completely random to your dependent variable. Second, the independent variables are linearly, I had to take a second to try at that, linearly independent. So if you have multiple independent variables, they should be independent from each other So the fact that my girlfriend broke up with me should be independent from the fact that I could not have a bathroom break. Okay? There's also that linearly part in there. All right. We are assuming a lot in terms of these relationships that they are linear, because if you're kind of predicting the slope of a line and your relationship is not in a line format, that's not going to work so well. 3, we got to get rid of that error term. So we're going to expect that the errors are 0. There's a really big word, heteroskedasticity, that if I was really mean and evil, I'd make you learn how to spell. Heteroskedasticity is the condition under which the errors, so the little line that deviates from your expected or predicted and your observed, that there's some sort of pattern in that. So you want the errors to be random. You don't want there to be a pattern in your errors. Homoskedastic. And finally, that the errors themselves are not correlated with each other. You get that a lot if you have time variables. Because what's the best way to predict today's weather? By knowing what yesterday's weather is. So we don't want correlation in our errors. Now, you can violate the hell out of these assumptions, but you just have to fix it. Right? So if time is a reason that your errors are correlated, then you have to incorporate time into your model. If the errors are homoskedastic, that's good. If they're heteroskedastic, that there's a lot of variance in the errors, that means you're probably missing a variable. And you need to find out what that variable is to get your errors under control. Or maybe you're even measuring your independent variable wrong. Okay.